time. It's the silent rhythm of our lives, an invisible thread that weaves through every moment, every experience, and every memory. It is the backdrop against which the drama of our existence unfolds, a constant companion that never leaves our side. An unceasing current sweeping us from cradle to grave, time is both a relentless force and a gentle guide. It shapes our days and nights, our seasons and our years, marking the passage of our lives with its steady, unyielding beat. But what is time, really? Is it a tangible entity, something we can measure and quantify, or is it an abstract concept, a construct of the human mind designed to make sense of the universe around us? Is it a river flowing eternally, as Newton believed, carrying us inexorably forward? Or is it something more complex, more intertwined with the very fabric of the cosmos itself? Or is it more like a cosmic dance, a fabric woven together with space itself, as Einstein's theory of relativity suggests, a dynamic interplay of matter and energy, where time and space are inextricably linked? From the ticking of a clock to the grand cycles of the cosmos, time shapes our perception of reality. It is the measure by which we gauge the duration of events, the intervals between moments, and the progression of our lives. It dictates the order of events, the cadence of our memories, the very essence of our existence. Without time, there would be no past, no present, no future, only a chaotic, timeless void. We experience it linearly, a relentless march from past to present to future. Yet, some theories suggest that time might not be as straightforward as it seems. Could it be that our linear perception is just one way of experiencing a more complex reality? But could our perception of time be an illusion? A mere shadow play on the walls of our minds? Could it be that time is a construct, a framework we impose on the universe to make sense of our experiences? The quest to understand time has captivated philosophers and physicists for millennia. From ancient thinkers to modern scientists, the nature of time has been a subject of endless fascination and debate. It's a journey that takes us from the everyday to the extraordinary, from the mundane ticking of the clock to the profound mysteries of the universe. Each step brings us closer to understanding the true nature of time, from the familiar tick of the clock to the mind-bending realm of black holes and wormholes. These cosmic phenomena challenge our understanding of time, bending and warping it in ways that defy our everyday experiences. Join us now as we delve into the heart of this enigma, exploring the depths of time's mysteries. We will journey through the corridors of history, the realms of science, and the frontiers of theoretical physics, exploring time's profound mysteries and the potential for a paradigm-shifting tipping point. Together, we will seek to unravel the enigma of time, to understand its true nature, and to glimpse the infinite possibilities that lie beyond. For centuries, the prevailing view of time echoed the words of Isaac Newton: absolute, true, and mathematical time of itself, and from its own nature, flows equably without relation to anything external. Time, in this classical Newtonian framework, was a constant and unwavering metronome ticking away in the background of the universe. Imagine a giant clock face, its hands moving at a steady, unchanging pace. This was the Newtonian view of time, a universal timekeeper governing all corners of the cosmos. Time was an independent entity, separate from space and unaffected by the events unfolding within it. This view resonated with our everyday experience. The clock on the wall ticked at the same rate regardless of whether we were sitting still or moving. Time, it seemed, was the one constant in a universe of change. Yet as physicists delved deeper into the fabric of reality, cracks began to appear in this seemingly unshakable edifice of Newtonian time. The universe, it turned out, held far more surprises than this straightforward picture could accommodate. In the early 20th century, Albert Einstein shattered the Newtonian view of time with his groundbreaking theories of special and general relativity. Before Einstein, time was considered a constant, an unchanging backdrop against which events unfolded. Newtonian physics treated time as a separate entity, independent of the physical universe. However, Einstein's theories introduced a radical new perspective. Time, Einstein revealed, was not absolute but relative, intimately interwoven with space to form a four-dimensional fabric called space-time. This concept fundamentally altered our understanding of the universe. Instead of viewing space and time as distinct entities, Einstein showed that they are interconnected, forming a single continuum. Imagine a trampoline as a representation of space-time. A bowling ball placed on the trampoline creates a dip, a curvature in the fabric. This analogy helps us visualize how massive objects influence space-time. The more massive the object, the deeper the curvature it creates. Similarly, massive objects like stars and planets warp the fabric of space-time around them. This warping effect is not just a theoretical concept. It has practical implications for how we understand gravity and the motion of celestial bodies. This warping of space-time, Einstein showed, is what we experience as gravity. When we feel the pull of gravity, we are actually experiencing the curvature of space-time caused by a massive object. This insight was a monumental shift from the Newtonian view of gravity as a force acting at a distance. And just as gravity affects objects in space, it also affects time. The presence of a massive object can slow down the passage of time, a phenomenon known as gravitational time dilation. This means that time itself is flexible and can be stretched or compressed depending on the gravitational field. Time, it turns out, is not immune to the distortions of space-time. The closer you are to a massive object, the slower time moves. This effect has been observed in various experiments and has profound implications for our understanding of the universe. One of the most startling predictions of relativity is time dilation. This phenomenon occurs not only in strong gravitational fields but also at high velocities. As an object approaches the speed of light, time for that object slows down relative to an observer at rest. Time, Einstein revealed, slows down in stronger gravitational fields or at speeds approaching the speed of light. This means that astronauts traveling at high velocities or near massive celestial bodies would experience time differently than people on Earth. Imagine two identical clocks, one placed on the surface of the Earth and the other launched into orbit. Due to the difference in gravitational pull, the clock in orbit will tick slightly faster than the one on Earth. This is a direct consequence of gravitational time dilation. Due to the difference in gravitational pull, the clock in orbit will tick slightly faster than the one on Earth. This effect, while seemingly bizarre, has been experimentally confirmed numerous times. Scientists have used highly accurate atomic clocks to measure these differences, providing concrete evidence for Einstein's theories. This effect, while seemingly bizarre, has been experimentally confirmed numerous times. Experiments involving atomic clocks on airplanes and satellites have consistently shown that time dilation is a real and measurable phenomenon. These findings have profound implications for our understanding of time and space. Time, as Einstein revolutionized our understanding, was not a rigid, unchanging entity, but a fluid, malleable aspect of the cosmos. This new understanding of time has opened up a myriad of possibilities for exploring the universe. From the bending of light around massive objects to the potential for time travel, Einstein's theories continue to inspire and challenge our perception of reality. Einstein's theories revolutionized our understanding of time, but they also opened the door to even more profound questions. His groundbreaking work on relativity showed us that time is not a constant, but a variable that can stretch and contract depending on the speed and gravity of an object. This was a monumental shift from the Newtonian view of an absolute, unchanging time. But as we delve deeper into the mysteries of the cosmos, we find that Einstein's theories, while incredibly powerful, are just the beginning of our journey into understanding the true nature of time. What happens at the extreme edges of our current understanding, in the heart of a black hole, or at the very beginning of the universe? These are places where the known laws of physics break down, and our current models fail to provide clear answers. In the singularity of a black hole, for instance, gravity becomes so intense that it warps space-time to an infinite degree, creating a point where our equations no longer make sense. Similarly, the Big Bang represents a moment of infinite density and temperature, a starting point from which time and space as we know them emerged. These extremes challenge our understanding and push us to seek new theories that can encompass such phenomena. Could there be a point where time itself reaches a tipping point, a cosmic crossroads where our current models break down? This idea suggests that time might not be an endless linear progression, but could have critical junctures where its behavior changes dramatically. Imagine a cosmic hourglass, where the flow of time is smooth and continuous until it reaches a narrow point, a bottleneck, where the flow is altered. This could be a moment where the fabric of space-time undergoes a fundamental transformation, leading to new and unexpected phenomena. Imagine a pendulum swinging back and forth, reaching its highest point before reversing direction. This simple motion can serve as a metaphor for the cyclical nature of time that some theories propose. Just as the pendulum reaches a peak and then swings back, time might also have moments of expansion and contraction. This cyclical view of time suggests that the universe could go through phases of growth and collapse, much like the rhythmic motion of a pendulum. Could time in some cosmic dance behave similarly, reaching a point of maximum expansion before contracting or even cycling back on itself? This idea is not just a poetic notion but is rooted in some of the most advanced theoretical physics. The concept of a cyclical universe where time and space undergo endless cycles of birth, expansion, and collapse offers a fascinating alternative to the traditional linear view of time. It suggests that the universe might be eternal, with no true beginning or end but rather a series of infinite cycles. The idea of a tipping point in time is still highly speculative, residing firmly in the realm of theoretical physics. Yet it is a concept that captures the imagination and drives scientific inquiry. Researchers are constantly developing new models and conducting experiments to test these theories, hoping to uncover evidence that could support or refute the idea of a cosmic tipping point. The pursuit of such knowledge pushes the boundaries of our understanding and challenges us to think beyond the conventional limits of time and space. Yet, it's a tantalizing concept that pushes the boundaries of our current understanding. The notion that time could have critical points where its flow changes direction or behavior is both intriguing and perplexing. It forces us to reconsider our most fundamental assumptions about the nature of reality and the universe. As we explore these ideas, we are reminded of the vastness of the unknown and the endless possibilities that lie ahead in our quest to understand the cosmos. Some theoretical models, like those exploring the Big Crunch scenario, suggest that the universe's expansion could eventually reverse, leading to a contraction back to a singularity. This would be a dramatic shift from the current understanding of an ever-expanding universe. The Big Crunch posits that gravitational forces could eventually overcome the expansion, pulling everything back into a dense, hot state, similar to the conditions of the Big Bang. This cyclical model of the universe offers a compelling vision of cosmic rebirth and renewal. In this scenario, time itself would reverse as the universe collapses, ultimately reaching a point where the very concept of time might cease to have meaning. This reversal of time challenges our conventional understanding and opens up a realm of possibilities that are difficult to comprehend. It suggests that time, like space, is a dynamic and flexible dimension that can be influenced by the forces of the universe. As we continue to explore these ideas, we are reminded of the profound mysteries that still await us in the vast expanse of the cosmos.